So a scatter plot might be enough for us to describe the relationship between two quantitative variables, but if we want to predict the value of one from the value of the other, then we're interested in what's called regression. So looking at this is a scatter plot with a regression line. We're looking at diamonds, and our explanatory variable is the size of the diamond in carats, and the response variable is the price per carat. So note that this is not the total price, which of course would increase with the size of the diamond, but even the price per carat does seem to increase with the size of the diamond. So looking at this, if we wanted to predict the price per carat of a 2-carat diamond, I would start by identifying 2 carats down here on the explanatory axis and trace up to the graph, and from there trace horizontally over to the response axis and try and estimate this value. It looks very close to the middle of 10,000 and 12,500, so maybe I'll just guess this to be 11,250. That's pretty expensive. Next question is, should we use this regression line to predict the price per carat of a 5-carat diamond? When I try to locate 5 carats on here, I'm up at 3.5 at the end of my graph and at the end of my data set. Then this would be 4, 4.5, 5 would be way out here. If I were to use this line to predict the value of a 5-carat, or the price per carat, I should say, of a 5-carat diamond, I would be assuming something really important. I would be assuming that this pattern continues. But the reality is that we don't know what's going on out here, right? So we don't know that this pattern continues. And therefore, we should be very cautious about any sort of estimation that we do outside of our data range. And I would say no in general. This is what you would call extrapolation, because instead of taking something that's between two known values, we're going outside of all of our known values. Generally, a tiny bit of extrapolation is probably okay. Like 3.5 is slightly out of our known values, but we could probably safely assume the model still holds. But wild extrapolation, like going all the way out to 5, we should not. It may well be that, in fact, the price per carat starts to increase at a faster than linear rate as you get out there. Or it could be that it starts to taper off because nobody has that kind of money, right? It's really anyone's best guess. Now this regression line does have an equation, and the general form of the equation is y hat equals a plus bx. We call this y hat because it's really an estimate of y based on x. It's not an actual y data value. So this is an estimate of our response variable. We use y for the response variable and x for the explanatory variable based on an actual value of x. So this is my explanatory. Now the two letters in here, A and B, also have interpretations. The b, which gets multiplied by x, is the slope of the line. That's a measure of how steep the line is. You might remember this from basic algebra classes. And the a is what we would call the y-intercept. That is when x is equal to 0. What is our prediction of y, right? So, one thing that is a little bit difficult for people who are familiar with algebra when they come over to statistics is that the formula you would have seen in algebra was y equals mx plus b, where m was the slope and b was the y-intercept. Now, not only do we have different letters, but one of the letters is the same, and it's being used for the other constant, right? In this formula, b is the y-intercept. In statistics, b is the slope. And it's because the pattern that we follow for linear regression continues on when we get into higher order regression, and we just keep following the alphabet for the coefficient of each term. So we can just forget about this guy that we knew in algebra. You know, some of the things that we learned from it are still going to be helpful, but it's not the same letters that we use to refer to it. So we get our information about this regression equation directly from the summary statistics, which come up in two quantitative variables in StatKey. We get these from the bottom of this box here. That slope there is my b, and that intercept is my a. So I can create my equation directly from this. That is y hat equals, my a is 1267. I don't think we need the 0.005. Our numbers are big enough that it's reasonable to go ahead and round them off. So we'll go ahead and round that up to 8. So my slope is 4978. And then I would multiply that slope by the explanatory variable. If I want to use this formula now to estimate the price per carat of a 2-carat diamond, what I'm going to do is plug that 2 in for x, because the explanatory variable is the size of the diamond in carats, and then just calculate y. So this becomes y hat equals 1267 plus 4978 times 2, which we can now bring a calculator in to help us with. 1267 plus 4978 times 2 gets us 11,223. If we look back at our estimate from the graph, we see that we had 11,250. So we were actually very close. Another way that you'll frequently see these regression equations written is, instead of with x and y, with the names of the response and explanatory variables. In this case, our response is price per carat, so I would just write that in as price per carat, however it would be stored in the computer, which is all squished together. And then the hat looks kind of funny because it goes over the whole thing, equals 1267 plus 4978 times the explanatory variable, which is carats, or a size actually, I think. Yes, size in carats. So that's a multiplication, all right, times size. Either of these forms is okay for your equation, right? Either the y hat with the x or the one using words. Sometimes with software, your output will automatically go for this second one so that it's very clear what variables it used to come up with that equation.